Welcome back, folks. We're still looking at Thevenin equivalent circuit problem, and it's our first one, so we're going a little slow. I'm chopping it up into extra videos. For this one, we are going to start finding the Thevenin resistance. And I promised you there's 3 ways we're going to do that. You're getting more than I got when I learned this originally. Just trying to give you your money's worth. Okay, so it's going to be the same problem. Let's go take a look at it. And it looks like this. Okay, so hopefully it feels familiar. We found the Thevenin voltage in the previous video. We found it to be 8 volts. We got to go find the Thevenin resistance. And this is going to be the first of 3 ways. So these are my names. If you go out into the world and you say, oh, how did you find the Thevenin resistance? And you say, oh, I used method 1. People are going to look at you funny. Okay, but there are 3 methods to do this. And we're going to do them in order. So I'm just going to call this method 1. And what we're trying to do here is find our Thevenin. Okay, so there's a limitation to this method, and I like to state the limitation to this method right up front. Okay, because if you don't, it might get lost. You should know when this method works and when it doesn't work, and that's why there's 3 methods. Okay, so the limitation here is that your problem or your circuit, CKT, short for circuit, certainly not in English, circuit can't have dependent supplies. Okay, so if you find a dependent supply in your circuit, method 1's out the door. So why am I even bothering to teach you if it has this limitation? It's honestly because most courses, this is the only method you'll learn. A lot of your faculty, not naming names, this is the only method that they are aware of. It has this huge limitation. As soon as you introduce a dependent supply, so anytime you have an op-amp and you're modeling that op-amp, you can do that with a dependent supply. If you have a transistor and you have a dependent supply, if you have a control system, if you're talking in the mechanical side, you're going to do that with a dependent supply as well. All of those cases, method 1's out the door, but a lot of times it's the only one you learn. It's a shame. I'm going to teach it to you because I want you to go do well in your other classes. And you need to speak the same language as other people. And this might be the only way they know how to do it. But now you know that there's a limitation. If you see a dependent supply, cut it out. Don't use this method. It's as simple as that. Okay. So to do this, we start by removing the load if it's there. Right? Remove load if drawn. Okay. And then we replace all independent supplies. If you're using this method, they should all be independent supplies, right? Right? Okay. There should be no dependent supplies left in the circuit. Replace all independent supplies. Guess what you're replacing them with? With their ideal resistances. Just like we did with superposition. Okay, so a voltage supply, am I still on the screen? Yep, voltage supply becomes a short, and a current supply becomes an open. Not bad, huh? Okay. Almost there. And then we got to go do it, right? Find the equivalent resistance where the load was connected. Okay, so here's what this looks like in practice, and I'll even give you some insight into how textbooks talk about it. Okay, so we go ahead and we copy. The circuit once again, and let me clean it up for you a little faster. Okay, and find the equivalent resistance. So we copy the circuit, and we do a couple things. We remove the load if it's drawn. Okay, so we remove it just like we did before when we were finding the open circuit. But this time we got to go through and we got to turn off all the other power. So we remove this voltage supply. That was an independent voltage supply. We're going to replace it with its ideal resistance, which is a short. Okay, so that gets connected just like that. All right, and then these were the terminals. These were the two nodes where the load was connected and will be connected ultimately. So a textbook is going to say, hey, you're looking for the Thevenin resistance. You're looking for the resistance between those two nodes. Okay, and a lot of times they draw an arrow. They're like, hey, you're looking back into the circuit from where the load was connected. It's kind of a silly, you're not looking into the circuit. You're connecting your meter there, and you're seeing what the resistance is across those two terminals. But a lot of times they say you're looking into the circuit from there. So they draw R Thevenin and an arrow. I think it's kind of a goofy way to talk about it, but hey, they didn't ask me. Maybe someday they will. I doubt it. I really doubt it. Okay, so from here we play the same game. We got that we did back when we were learning series, parallel, neither, both. That's why it was kind of important to get really good at series, parallel, neither, both. So what components are in series? I don't see any. The 5 doesn't share a node exclusively with anything. You've also got to remember that we're connecting something out here. We're connecting a meter out there. So the 5 doesn't share a node exclusively with the 3 or the 6, nor does the 3 and the 6, right? Because there's going to be some current that flows out this way to the rest of to whatever load you're connecting to it. So nothing's in series. Is anything in parallel? Let's see. We can play the node game here. Let me get a bigger marker. That's really big. Okay, there's a node. Here's a node. Okay, and then since we're going to connect something out here, we can think of this as a node as well. Okay, I'll get rid of those in a moment, but we can see that the 3 and the 6 are both connected to the orange node and the blue node. So those are in parallel. Okay, so let's go ahead and redraw it. And, oh, that's huge now. Let's draw it with a reasonable size pen. Something like that. Okay. All right, so there's the 5 ohm. And then 3 in parallel with 6. Hopefully you're getting comfortable doing that we've done a lot since then. If you're not comfortable with that, you should go review a lot of these videos. Okay, so this is going to be 3 in parallel with 6. And that is equal to 2 ohms. Okay, and we're finding our Thevenin, and we're still finding our Thevenin looking back into the circuit from here. All right, circuit's pretty simple now, right? How are these connected to each other? Those are in series, so we can be a completionist and redraw the circuit as a single resistor, which is kind of what we're trying to do, although the drawing doesn't really add much to it. If these are in series, we simply add them together. 2 plus 5 equals 7 ohms. And that's our Thevenin. Okay, so our Thevenin equals 7 ohms. Not too bad. Not too bad. So we've got 8 volts and 7 ohms. That's our equivalent circuit. So we already know the equivalent circuit. But we also know that this method would fail if there was a dependent supply in the fixed circuit that we're trying to reduce. So we got to find a way around that. So we're going to abuse this example 2 more times, at least 2 more times. And we're going to use some other methods. What we're going to find is that we get the same result. The other methods can still be applied to this circuit. So we're in good shape there, but we're going to get that same result. this is a start. Stick with me. I'll make you really good at this. Okay, method number 2 coming up next. Stay tuned and good luck.